So we talked about the energy involved in the transition between a solid and a liquid. No, that's what we're talking about today. We talked about the liquid and the gas transition. Now we're going to talk about melting and freezing, which are the transitions between solid and liquid, and also sublimation, which is going directly from a solid to a gas. So if we take a solid and we increase the temperature, as the temperature increases, the thermal energy increases, the molecules or atoms vibrate faster, and when it gets to the melting point, then they have enough energy to overcome those intermolecular forces, the stick-togetherness that's holding them in a solid, and turn into a liquid. So they've broken loose enough to slide around. They're still going to be very close to each other. They're going to be a liquid, not a gas. When ice melts, the water molecules break free from this lattice structure. They've got this kind of open structure, and it's crystalline. And as the ice warms up, they're able to break free and swim around. They're still touchingly close, but now that it's a liquid. If you have the ice and water both present, the temperature will be 0 degrees. The temperature will not go up until all of the ice has melted, and that's similar to what we saw with water boiling. So at 1 atmosphere of pressure, temperature of ice and water will always be 0 degrees Celsius. And I think that's one of the reasons that 0 degrees Celsius is the standard temperature for gases. It's very easy to obtain. Get a big vat full of ice and water, and you don't even really need a thermometer. It's going to be at 0 degrees Celsius. So if we look at a heating curve during melting, it's going to look similar to what we saw during evaporation or boiling. Here, starting at -20, the temperatures, of course, have changed. And you warm up the ice, and the ice increases in temperature until it begins to melt, and then the curve flattens out, and the temperature will stay at 0 until all the ice has melted. And at that point, the liquid water will increase in temperature. When you add ice to a drink, you get some tap water and you put ice into the water, it cools the water, because what it does is the melting of that ice is endothermic, and it's sucking energy from the water, reducing its temperature. It will reduce the temperature down to 0 degrees Celsius, but it won't go any lower. Melting is endothermic. Energy has to come in. That makes sense to us. How do you melt an ice cube? Well, you warm it up with your hand, or you stick it on a heat source, right? The opposite process is freezing. Freezing is exothermic. It gives off energy. That is not immediately obvious to us. In your freezer, if you put water in there, it will freeze. That's why we call it a freezer, because it freezes things, right? How does it do that? It's extracting heat from the inside of the freezer. You have a condenser and a compressor and a fan, and it's sucking heat out of the inside of your freezer compartment, and that's why the temperature goes down. As the temperature goes down and the water temperature in there goes down, the molecules are moving slower and slower, and soon these intermolecular forces take over and it becomes a solid. So there's energy involved in melting and in freezing. Fusion is the fancy word for melting. And that's one that's not obvious to most of us. Heat of vaporization, okay, vaporizing something, turning it into a gas, that's fine. Fusion. The way I remember this is I think about chocolate chips. What happens when you melt chocolate chips? They fuse together, right? They were little bits of chocolate, and as you heat them up, they get soft and they fuse together. Fusing is melting. So heat of fusion, the amount of heat needed to melt 1 mole of a solid. Heat of fusion of water, 6.02 kilojoules per mole. So taking solid water, ice, and changing it into a liquid. Delta H is positive because it's an endothermic process. You take the perspective of the water and the ice cube, solid water, and in order to melt, energy has to come in. So that's a positive thing, like money coming into my wallet is positive. If we freeze the water, that's the opposite, going from a liquid to a solid. The amount of heat that is transferred is the same. It's 6.02 kilojoules per mole, but now the sign is negative because that energy is leaving the system. So the amount of energy is the same. The sign indicates what direction the energy is going. So we can use the heat of fusion to calculate how much heat energy is needed to melt a certain amount of a solid. You know, you've got a 5 kilogram ice cube and you want to know how much heat do you have to put in to melt it. That can be calculated. And we can also use the heat of fusion as a conversion factor between moles of a solid and the amount of heat needed to melt those moles of solid. So let's do an example. Calculate the amount of heat absorbed when a 15.5 gram ice cube melts at 0 degrees Celsius. So we said that the heat of fusion of water, delta H fuse, was 6.02 kilojoules, and that's per mole. That's a great little conversion factor between amount of heat and amount of substance in moles. This is specific to this substance, water. If you're going to do steel or something else, it's going to be different. So if we have 15.5 grams, that's too far over. Keep forgetting about this silly screen. Does that work? Not quite. We'll just have to write in the middle. 15.5 grams. And what unit are we trying to get to eventually? Something about heat. Could be calories or could be joules. It doesn't specify, so I'm going to go to kilojoules because I think that's going to be the easiest based on what I see here, this being in kilojoules. I have an amount in grams. This conversion factor would allow me to go from moles to kilojoules. So if I could get to moles in the middle, I could get to kilojoules. And we've learned how to convert from grams to moles. 15.5 grams times moles on the top, grams on the bottom, times kilojoules on the top and moles on the bottom. I want moles to cancel out. I want grams to cancel out. The number for this last factor is the heat of fusion, 6.02 kilojoules per mole. So I'll stick that in there, 6.02. And here in the middle, we need the molar mass of water. Ice is H2O. And I've used that one a lot, so I remember it is 18.02. And then we use the calculator. Here comes the train. 15.5 divided by 18.02 times 6.02. This should have 3 significant figures. And we're going to get 5.18 kilojoules of heat. Any questions? This diagram from your book shows a heating curve for water from minus 25 degrees Celsius up to 125 degrees Celsius. So we see that the ice warms up as heat is added. This is kilojoules per mole. As heat is added, the temperature of the ice rises until it gets to the melting point. At that point, you add more heat, you're melting the ice. Question?
I thought you said ice can't get colder than 0.
Good point. An ice-water mixture can't get colder than 0. but ice itself can get colder than 0. Yeah, there's a subtle but important distinction there. So here's very cold ice. As it warms up, it's still ice. It's not melting. Hits 0, starts to melt. All the energy that's being absorbed here is now going into melting the ice to form liquid water. Once it all melts, then the temperature can rise. And the temperature rises in a linear fashion until it gets to the boiling point. The water starts to boil. And you see how much longer this plateau is? It takes more energy to boil this amount of water than it did to melt the ice. It takes a lot more energy. So the temperature will stay the same until all the water boils away, and then the temperature of the steam will rise. So looking at a graph like this, you should be able to identify that this section right here is a mixture of solid and liquid. This is a liquid, and this flat part is a gas-liquid mixture. Any questions? Sublimation is another physical change. It's going directly from the solid state to the gaseous state. And we don't see this happen a lot, but it does happen. When a substance sublimes, the molecules on the surface, which are less tightly held than the ones inside, can go directly from the solid to the gas state. And only certain substances do this. Dry ice sublimes. Dry ice is called dry ice because it doesn't melt. It doesn't get everything wet. It's ice. It looks like ice. It's cold. It's solid. But it's actually solid carbon dioxide. It doesn't melt actually at any temperature under atmospheric pressure. The only way you can melt it is by putting a tremendous amount of pressure on it. So it will sublime at temperatures as low as minus 78 degrees Celsius. That is crazy cold. That's really, really cold. So the CO2 molecules are able to just leave. And that's what you see. What do you see when you see dry ice out in the air? See, it looks like there's like white smoke stuff coming off, right? And Halloween is just around the corner here, and so you're probably going to see somebody who's got like this big witch's cauldron, right? And they've got dry ice chunks in there. And it comes out and it looks like it's steaming and boiling, and yet it actually isn't. As that dry ice, as the CO2 sublimes, it's cold. And it causes the air to cool around it, and it causes the moisture in the air to condense. You can't actually see gaseous CO2. But because it's so cold, it causes like a mist almost from the condensation of the water in the air. And so that's why it looks like smoke. It's actually just water droplets. So this is what I'm talking about. Here they've got a big chunk of solid CO2 on a ring stand, and we see here that it's cooling the air and cooler air tends to fall, and so it looks like it's falling down, and it's causing the water in the air to condense, and that's why we can see it. But it will not melt. It just doesn't melt. Very, very fun stuff. But it's also so cold it'll burn your skin. It'll give you frostbite. Regular ice, solid water, also sublimes. It does so much more slowly, but it does this in your freezer. And in Minnesota, where I grew up, the snow sublimes. So maybe it snowed and the temperature doesn't get above 0 degrees Celsius. I mean, they sometimes go for weeks and weeks on end without the temperature getting above 32 degrees Fahrenheit. And the snow gradually disappears. The snowbanks get a little bit smaller and a little bit smaller. It's like, who's stealing the snow? Nobody's going around and stealing snow. It's subliming. Ice cubes, you leave them in the freezer for a really long time. You know, there's that tray that got forgotten in the back. You pull it out and it's like, who half filled this? What's going on here? They're so small. They've been subliming. What happens in your freezer that gets all over the sides? Frost, right? Unless you have a frost-free freezer, which hopefully you do, but if you've got one of those little dorm fridges, those things frost up really badly, don't they? Where does all that moisture come from that's freezing onto the cooling element? It comes from ice that's in your freezer. It comes out of your food. It comes every time you open the open the freezer, some moist air from outside comes in and that water will freeze and condense. But in your freezer, sublimation is going on. That's why ice cubes shrink. That's why, did you ever watch Arthur? There was an episode where DW put a snowball in the freezer. And then, I don't know how long, much long later, she was like so outraged because her snowball had disappeared. Right? Who took her snowball? It's sublimed. And why does your food get freezer burn? It gets all dried out. Or you've got a bag of tater tots or French fries, and you didn't eat them right away, and you finally remember them, or maybe you don't have anything left, right? So, we'll have tater tots for supper. You open the bag, and here's the tater tots, and there's all this ice in there. Who would put ice crystals in with the tater tots, right? They melt and they make everything all soggy. That water came out of the tater tots. It's sublimed. Went into the gas state in the bag inside your freezer. Because it was in a sealed bag, it couldn't get out. So it condensed, but not back inside of the tater tots. So, a couple ways you can avoid freezer burn on your food. If you wrap it very tightly, then when the water sublimes, it can't go anywhere, and so it's not going to sublime as much. And so that will help. Doing like a vacuum sealer or wrapping it in foil and then trying to get all the air out will help a lot. Or if you have a deep freeze where the temperature is lower than a regular freezer, the lower the temperature, the slower the sublimation. And so much lower temperatures like a sub-zero freezer will preserve your food longer. Anybody have any questions about sublimation? I think it's kind of cool. You didn't get that? So I kind of already said that. It was so bad, nobody even recognized it. Oh, okay, you just chose not to acknowledge it. That's fine. I'm not offended.